to get the units right, we're going to take 0.05 grams per liter, divide by 1,000, so we have now 5 times 10 to the negative 6 grams per milliliter. And that's what we're going to put for right here, so that we have milliliters right there, because this right here is going to tell us we're going to make liters. Alright, so if you examine the teacher's guide, this is what I'm supposed to use to grade student work. Right? There are no answers here. So if I'm looking at the data table you turn in, I have to know what the answers are in order to grade you right or wrong. So I had to do a little research on my own. Unfortunately, the lab aids kit is wrong. On the internet, it says that the density for stearic acid is 0.94. So if we look right here, it says, yeah, right here. Well, we have another source other than Wiki that it is 0.94. If you look up here at the top, 0.94 kilograms per meter cubed. So, okay, so we've calculated the volume for the first set of data that we need to calculate the height. So the volume is right here. This is where the volume goes. And it has to be in milliliters or centimeter cubed because the radius is going to be in centimeters squared, and you'll end up with a height in centimeters. Value for stearic acid is 1.7 times 10 to the negative 7. For sorbic acid, we got 5.18 times 10 to the negative 7. So I'm fairly confident that this answer is correct. Cody. The bell work today is associated with the lab we're trying to finish up from yesterday on the size of the molecules. I really do like this lab. It shows how the acid can form a different layer based on the bonding with the water. So up here we need to know that molar is grams per liter. So when you see on the paper here where it says capital M, they even have that written there for you. Does everybody see where I underlined in red? You might want to underline that as well. See where it says grams in 1 liter. That's what the capital M represents. Grams in 1 liter. Does everybody see that? So go ahead and underline that from the lab from yesterday. Get this out so that you can get, I'm trying to help you get full credit because there are mistakes on the lab. So if you write, okay, good. All right, so the problem is that the answer there is 0.596 milliliters. And they've given us, they said in this, what I underlined in red, that they give you 0.05 grams in 1 liter. So they have converted this without changing the value. I got the plan for the guide as far as the height from Yahoo. I searched on Yahoo. Now you have to remember that everything on the internet is not always correct as well. This right here is sternic acid, right? And if you look here, she's using a density of 0.94, right, for sternic acid. Now if you look on the paper here, sternic acid, the density is not 0.94, it's 0.85. So the density up there is wrong, or the density is here is wrong. So I'm going to probably say the density up there is wrong.
What's that acid? Because this is steric. You said something else.
0.85.
Steric.
What's hers up there?
She has it for 0.94. Right? So let's search the internet. There are some errors associated with this lab. If you look on this paper that I gave you yesterday, it says 112, that's 112, which would be the molecular weight for sorbic acid, times 0.005 grams in 1 liter, right? That's in 1 liter. Now, when you go down to the problem, it says 112 or 112 times 0.005 m, and then they give the answer in milliliters. Well, you can't do that. It's not the same unit. So milliliters and liters are not the same unit. There's 1,000 difference between the two. 1 liter equals 1,000 milliliters. Now, I only noticed that because the booklet, they send you a booklet with these labs, and there's usually an answer key, but there's no answer key in this one. Now, I'm not trying to say that this is a bad lab. I actually really like the lab, and I'll do it again. I'm just trying to improve it so I can grade you correctly. Because it's never good when I mark an X over a height that you calculated, which I actually did not know, and gave you an X for it, right? So I went on the internet and I did a little bit of a search and I tried to determine what was the height of one of these acids. And I found on Yahoo, I'll show you up here, a result for that. Let me pull that up on the internet. Okay, so here's our data for the graph. Our plots, we have 1, 2, 3, 4, 5. Rain did a nice job pointing out to me, Rain right there in the blue, that this was actually 32 and not 3.2. We wanted to get all of the scientific notation values the same, so when we plotted this, we didn't have to put the values on there. So it would be 2 times 10 to the negative 7. So 32 is way up here. This is an outlier. That means it's not consistently closer to the other data. That means there's probably something wrong here in the lab. Maybe this value wasn't calculated correctly, or our math might actually be wrong. So we're going to check our math here real quick to make sure that answer's right. All right, so it's going to fall right next to the value for 5. You can see here, these are the calculated values. We notice 2 additional errors with the density. It's actually 1.2 grams per milliliter for sorbic acid and 0.94 grams per milliliter with stearic acid. So today, if you follow along and you record what we are going over, then you're going to get full credit on this lab. That would be 100%, because I'm telling you the answers basically. So 454 grams equals a pound, and a liter, if you don't know what a liter is, it's just half a 2 liter. A 2 liter beverage bottle has got 2 liters in it, so just half of that would be a liter. So the capital M represents grams per liter. So what you're going to do now, you're going to copy this data down. We're going from grams per liter to milliliters. Now, in the data sheet that they had, they just took this value times this value and stated that this was how many grams were in this solution. This molar solution is this many grams. And they multiplied it times the density, so you have milliliters. If you notice here, the grams cross out. My steps here leaves the milliliter in, but I'm just showing you what they did, so it makes sense to you. Nice job. All right, so we're going to plot on a graph the y for the height, and we're going to plot the x grams per drop on the graph. So this is what the graph looks like. Now what we did, we converted the units so they're all 10 to the negative 7. 10 to the negative 7. So the unit here is going to be grams per drop, 10 to the negative 7, 10 to the negative 7 centimeters. Right, Rain did notice there was an error in our data calculation. It should be 0.31 times 10 to the negative 7. So this outlier is incorrect. It's going to fall back down here. We'll apply it here in just a second. Okay. Okay, you see 4? You're supposed to see 5.
Okay, I see 4.
That's good.
Are you looking with your eyes?
Look to the right over here, and if you push this button, if you push the button, you'll see the gradient or the numbers.
Oh, I see that. Yeah.
How many you see?
Did you do this in Thompson? You should have.
On the left.
We're going to graph this data here in a minute. My main concern is for h, which would be the height, and the volume, because those two things are necessary to calculate the height value. You need the volume. That was the problem yesterday. That was our error yesterday. We're also going to calculate.
Are we running into space below?
You can, yeah. We're going to calculate this value for x, which is the number of drops per gram. We're not going to do number of carbon atoms in a drop. Why aren't we going to do the number of carbon atoms in a drop? Noah, why wouldn't we want to do the number of carbon atoms in a drop? Okay, we have 5 acids here, right? 5 acids. Do those acids have other elements besides carbon?
Yeah.
Yes. What is the other most common element in an acid besides carbon? Raise your hand. No. Oxygen. The oxygen isn't an acid, yes, but it's not the most common.
Nitrogen.
What do acids do? They are considered to be blank donors. What? Hydrogen. Yes, hydrogen is the most common other element in an acid. Acids are hydrogen donors, and when you stick your hand in an acid, guess what it's doing? It's hitting you or giving you, like Alex said, it's giving you hydrogen. It's basically hitting you. Lots of them. And you're like, that's starting to hurt. Ow, that hurts. It's like you're getting punched in the face, you just can't see them. They're just punching you in the face. Or wherever you get the acid on you. So, because they've got other things in there, we'd have to isolate the carbon atoms only, and I'm not going to do that. That's more math than I have to put up on the board up here, and it's just not necessary at this stage. Maybe if we were in February or March, we'd take a look at that, but at this early in the game, we're not going to go there. We haven't really talked about molecules in the mole yet as far as mathematically, so we're going to keep it simple and not go that route. Now this up here is simple because you're following the unit. When you go into math, the unit is your best defender. Like when you're in algebra, they don't teach you this, but when you go to business or economics, follow the unit because it will lead you back to where the error is. Like yesterday, my error in the lab was dividing by drops, and you can't put drops over here. Drops doesn't fit into this equation. It has to be centimeters. That was an error in my part. So up here on the overhead, the dilemma of the atom. Electrons outside the nucleus are attracted to the protons in the nucleus. Most of you know that. But like when you were in middle school and you learned about the planetary model of the atom, that was the one that, who came up with the planetary model? I remember. Gold-Full experiment?
Rutherford.
Rutherford. Right, so Rutherford, points. Rutherford, he came up with that model. Before that model, you had J.J. Thomson and the plum pudding model. I would have called it the chocolate chip cookie model. Because if you look at it, it kind of looks like a chocolate chip cookie. What kid wouldn't, think of chocolate chip cookies? That would be a better model for kids to remember. That would be J.J. Thomson and the chocolate chip cookie model.
Is it because it has all those dots on it?
Yeah, they're kind of everywhere. Yeah, chocolate chip cookie. Yes. So when you were learning in middle school about the planetary model, right? And then they switched models, and what model did they go to next? What came after the planetary model? Anybody know? No. It's called the electron cloud model. There's kind of a cloud where the electrons are in orbits using a wave form of movement. So the problem here with the planetary model is that they're moving around in kind of like circles. Is everybody clear? There's a difference between moving in a circle and moving in a wave. Yeah, so this right here, it says charged particles moving in curved paths lose energy. So if it just kept moving in a curved path, like around the planet, it's going to lose energy. And that's the reason why that model was dismissed. That is no longer accepted. The planetary model's dismissed because of charged particles moving in curved paths lose energy. A hydrogen bomb today because North Korea, if you've been following the news, they want to explode one of these in the ocean. I think it may be the Pacific they want to drop it in. I'm not sure.
Would that contaminate the water?
Yes. It could, but it would kill a lot of fish. Yeah.
Why are they doing that? They're
Because they want to show this better.
So stage one, the primary ignites,
How do they even make nuclear?
creating a foam. Stage three, the plutonium spark plug begins fission.
You know they can't see it on the ground.
Then a fireball. Yeah, you can see that.
They can't.
Yeah, the fireball starts to form. And then you got
Oh,
Can you go back?
explosion.
next time.
That's if you know what Henry Moseley did. What did Henry Moseley do? You might know? Vance, what did Henry Moseley do?
Henry Moseley was the key factor in chemistry history.
What did he do?
He did a lot.
Okay, so write this down. Henry Moseley determined the number of protons in the atom. Henry Moseley determined the number of protons in the atom, the atomic number. This was done less than 100 years ago. So it's a relatively new concept. Less than 100 years? Yeah. Our country is like 200 and something years old. Right. And the proton is the atomic number, it determines the look, right? Now, what did he use? I'll give you 15 points if you can tell me. What did he use to determine the number of protons in the atom? Raise your hand. No.
Wait, did he use that behind you?
No, what did he use to determine the number of protons in the atom?
Rays.
Raise your hand. Raise, no. Raise your hand. TT? Electrons. Very good. 15 points. Okay, so once again, M on the sheet, right? It says 0.005 M. The M, 0.05 M, which is right here, corresponds to grams per liter. Grams per liter. So then what we're going to do, we're just going to get that into milliliters. Liters cross out, and then you have milliliters. So we got right here grams in a milliliter, and we're going to multiply it times 1 over the density to get rid of the grams. So we have our milliliters. That gives us the volume.